Welcome back, guys, and what we're going to be looking at in this tutorial is a geometric sequence. So in the last two tutorials we've been looking at arithmetic, where it's all about addition and subtraction. Today what we're looking at is a geometric sequence which focuses on moving from term to term by multiplying. Now if you go to page 22 in your log tables, again you'll see on the right hand side of the page where it says geometric sequences and series, and specifically you'll see where it says Tn is equal to a by or to the power of n minus 1, and this is a power n minus 1. Now most things stay the same. A is our first term, T1. Or stands for our common ratio, which is one term over the term before it. So for example, T2 over T1, which in general can be written as Tn plus 1 over Tn. And again, this is the rule we're going to use to prove that a sequence is geometric. Now, if we look at the first one here, it says find Tn and T10 of the geometric sequence. Now they're kind enough to tell us that it's a geometric sequence this time, which means we need to recognize that when it's geometric, we're using Tn is equal to a or to the power of n minus 1. And we're looking to see what is my ratio, my or, moving from term 1 to term 2. So to start off, nice and basic, still the same, we can see a is equal to 1. Or, which is my common ratio, I can find by putting term 2 over term 1, which would be 1 over 4 over 1, which I can see is just 1 over 4. So my common ratio now is 1 over 4, or a quarter. So now I can say, therefore, Tn is equal to a or to the power of n minus 1, which means I have 1 in brackets 1 over 4 to the power of n minus 1. And those brackets are important here because only the 1 over 4 is to the power of n minus 1. Our term for a is not to the power. So now to find T10, all we have to do is, again, anywhere we see an n, we're going to sub in 10. So we're going to have 1 by 1 over 4 to the power of 10 minus 1, which gives me 1 over 4 to the power of 9, which we're going to put into our calculators here, as 1 over 4 to the power of 9 gives me 1 over quite a large number, 262,144. Okay, so take a second here, go back through example 1, pause the video, and then when you're ready, we'll move on to example 2. So very similar to what we were looking at when we looked at arithmetic sequences, we're now going to use our formula, our general formula, to find a and or. So it says in a geometric sequence, which again they were kind enough to tell us, so we know we're going to be using this formula. T3, so term 3, is equal to 32. So just like when we were looking at our arithmetic sequences, I'm going to write down my general version for Tn. I know that the value of Tn is 32, so I have 32 is equal to a, or instead of n, I'm going to sub in 3 minus 1, which means 32 is equal to a or squared. I'm now going to do the same thing for T6 is equal to 4. So I have Tn is equal to a or n to the minus 1. So I have 4 is equal to a or 4 to the minus 1. So I have 4 is equal to a or to the power of 3. Now at this stage I can see I can't go straight into simultaneous equations because it's multiply here. So what I'm going to do is I'm going to look over here and I can see that a isn't squared, so a is easier to isolate. So I'm going to divide both sides by or squared to isolate my a, which gives me 32 over or squared is equal to a, which I'm now going to take and sub into my second equation. So I have 4 is equal to 32 over or squared by or cubed, which if I look over my rules of indices, when I have or cubed over or squared, I minus the powers, which is going to give me 32 to the power of or, because they cancel to leave me to the power of or, which means now I'm going to divide both sides by 32, which means that I'm going to get that 1 over 8 is equal to or. which now I can sub back in over here to find my A. So this is going to give me 32 over 1 over 8 squared is equal to A. So this gives me, oh, sorry, I see a mistake here. What I should have had back here is that n should have been 6. So you can see here how this is going to change what we're doing just a little bit. So if n was equal to 6 up here, I would have had 6 minus 1, which would have given me or to the power of 5. When I did or to the power of 5 minus or to the power of 2, that would have left me with or cubed. Which means when I got down here, what I should have done to both sides is cubed root both sides. Apologies. And when I cubed root both sides, what I would have been left with is a half is equal to or. So over here, what I should have subbed back in is simply that 32 over a half to be squared, which now I'm going to put into my calculator, gives me 128. So my first term is 128 and my or is a half. Apologies for the little math error there. So I found A and or, which is the first part of my question here. And part 2 then says, hence write down the first 6 terms in the sequence. Well, again, I've found my first term now, which is that A is equal to 128. And I know that to go to my next term, what I need to do is multiply by my common ratio, which is a half. So I know that 128 times a half will give me 64, and I continue to times by a half. So 32, then 16, then 8, then 4, then ... And we go from there. So guys, you might want to pause the video here, particularly after my little arithmetic error there. Go back through example 2 and then we'll move on when you're ready to example 3. And example 3 is very similar to a question in the exam papers just before the factor theorem. So let's have a look here. It says we have 3x and x plus 6 are the first 3 terms of a geometric series. And we know that it's a geometric series of positive terms. Now when they give us that piece of information, we know it's going to be crucial. Now, find the value of x. This is where we need to remember that for a geometric series, or is equal to term 2 over term 1. But it really means that any term over the term before it would be the same. So that really means that's equal to term 3 over term 2 as well. So if we look here as this being our term 1, term 2 and term 3, for part 1 here, what we can actually do is set up our rule to solve it. Where I have term 2 over term 1 is going to be equal to term 3 over term 2, and then all I need to do is substitute in. So I have x over 3 is equal to x plus 6 over x. I'm going to take now both sides and multiply it by the denominator of each fraction to get rid of my fractions. So I multiply by 3 on both sides and I multiply by x on both sides. I can see on the left hand side my 3's are going to cancel, and on the right hand side my x's are going to cancel. So I get x by x is x squared is equal to 3x plus 18. So I have a nice little quadratic now, so I'm going to move everything to the same side and solve my quadratic. Now when I solve my quadratic, I can see I'm going to use 6 and 3, negative and a plus, so I'd get x is equal to 6 and x is equal to minus 3. But of course, because I spotted this positive terms at the start, I know the only one I'm going to accept is x is equal to 6, and I'm not going to accept x is equal to minus 3. Part 2 asked me to find the 10th term, so it's really asking me to find T10. And so to find the 10th term, I'm going to start off by finding Tn, which would be a or n to the minus 1. To do that, I can see that I have my sequence, which was 3, then x, which means it would be 6, and then x plus 6, which I know would give me 12. So I can see a is going to be 3, and to get to the next term, what I'm timesing it by each time is just a simple 2. So that means I'm going to have 3 by 2 to the power of n minus 1 as my formula. So that means to find Tn here, instead of n, I'm going to substitute in 10. So I really have 3 times 2 to the power of 9, which I'm going to put into my calculator now. So I have 3 by 2 to the power of 9, which gives me 1536 is my 10th term of the sequence. Alright, so again guys, we only have one more example here for my geometric sequences. So if you want to pause for example 3, then we'll move on to example 4 before we start looking at our geometric series. Now, oh sorry, we have 5. My apologies. For geometric sequences, the next one has a bit of a trick. It says the product, and we know that the word product means to multiply, of the first 3 terms of a geometric series are 216, and their sum, which I know means to add, is 21. Well, we know guys that in a geometric series that a is my first term, but if I was to use the next 2 terms, it would be a or, because it's times by or, and a or squared, which when I'm going down to do product, I know is going to get a little bit difficult. So I know the next term would be a or, because I multiply by or to get to my next term. And if I'm multiplying by or to get to my next term, what I'm going to do is a little trick here, where I'm going to divide by or to get to the term before that, which would be a over or. Because now when it looks to using what they've given me about the product, it's greatly going to simplify what we're doing here. Because that means term 1 is going to be a over or times a or is equal to 216. Which means I'd have a cubed over or. A cubed or over or would give me 216. Which means nice and simply here, my ors would cancel, which it wouldn't if I hadn't used this little trick. So now I'm going to get a cubed is equal to 216. And to get a, I simply cube root both sides. And when I cube root both sides, remember pressing shift and square root on your calculator, it gives me 6. So I have a now is equal to 6. So now I'm going to use the other piece of information they gave me, which is the sum. So again now, looking at my sequence that I had here, I now have 6 over or, 6, and 6 by or, substituting in for a. And they're telling me that if I add these together, that it's going to give me 21. But before I do this, what I can see is here that this is going to end up as an algebraic fractions question. So I'm going to multiply by or to get rid of the fractions, which would give me 6 plus 6 or plus 6 or squared is equal to 21 or. So now I'm going to rearrange it here to get my nice little quadratic, and I'm going to solve for or. So I need an or in each bracket. I know my factors of 6 are probably going to be 3 times 2. And if I want to get 15 here, what I'm actually going to do is have a 6 here and a 1 here, because 6 by 2 is 12, 1 by 3 is 15, and they're both going to be a minus. Which means here I'd have or is equal to 2, and here I'd have or is equal to a half when I bring it over. Now guys, this is where we have a trick. Because in the question, which I didn't read out at the start, it says given that the common ratio or is less than 1. So if it's less than 1, that means it has to be a fraction. So we're going to accept that or is a half, and we're going to reject that or is equal to 2. It says find the first 3 terms of the sequence. Well, now I can go back and I can see my first term is 6. To go to the next term, I'm going to times by a half, which would be 3. And to go to the next term, I'm going to times by a half again, which would be 3 over 2. And so now I have my 3 first terms nice and simply. No, I don't. Apologies. What I should have done here, which would have corrected this, is what I forgot is that a is actually not the first term by the way I've set up this equation. So what I need to be doing is having 6 over or. Do we see this at the start? 6 over or, so if I have 6 over a half, that would give me 12. Then I would have 6 in the center as I had here, and then 6 by a half, I'd have 3, ... Apologies guys, nearly made that simple arithmetic error again. As we all know, we learn from our mistakes, so these are important little things to catch as we go along, which is important to do as you look over your work, as I did there, to catch those little errors. Alrighty? So when you're ready, we have one more example, and then we're going to wrap up on geometric sequences to start looking at geometric series. So the last one here, example 5, says find the number of terms in a geometric sequence that starts on 81, 27, 9 and goes up to 1 over 27. So this one is going to be important, okay? Because again, it's asking me how many terms, so it's asking me really what is n. It's told me it's geometric, so I know that Tn is equal to a or to the power of n minus 1. I can see that my a is going to be 81 because it's my first term. My or would be my second term, which is 27 over 81, which we always simplify now before we go any further. So 27 over 81 gives me a third. So I have a third n to the minus 1. But they've told me that Tn that I'm looking for is 1 over 27. Now we have a messy little bit of algebra here to try and find n, so let's stay with me here. The first thing I'm going to do is try and get rid of this 81 because it's out here and it's not with the n. So to get rid of this times by 81, I do the opposite. So I divide both sides by 81 here. So again, on your calculator, you have 1 over 27 divided by 81, which gives you 1 over 2187 is equal to 1 over 3 to the power of n minus 1. Now, at this point I can see I'm looking for a power, and we all know in algebra when I'm looking for a power, what I'm really going to use is my logs. So again, if you go to page 21 in your log tables, you'll see your key rule here. A to the power of x is equal to y. And if we're looking for x, we can now say, using our arrows, that log a of y would be equal to x. So to rearrange my formula here to make it look the same, I'd have 1 over 3 n to the power of n minus 1 equals 1 over 2187. I draw my arrows just like I did up here, which would be just like this. So now I can say log of 1 over 3 of 1 over 2187 is equal to n minus 1. So again, using the log button, which is just under the on button on your calculator, I have log of 1 over 3 of 1 over 2187, which gives you 7, is equal to n minus 1. Bring over my 1 to get 8. So now I have, therefore, term 8 is equal to 1 over 27. So this is the key trick when using geometric sequences, is that it's going to come back to one of our favourite bits of algebra that we can never get away from, is our logs. So particularly with this question, guys, can we take a few minutes to pause the video, go back over it, make sure we understand how to apply our logs, maybe go back over the tutorial videos we did on logs before we try a few questions.